Well, welcome back to our study of networks and distributed systems based upon the textbook by Jim Carose and Keith Ross entitled Computer Networking, a Top-Down Approach. We're starting lesson 3 now. We've already completed the first 2 lessons on this fifth module on the link layer. In the last one, we had begun to discuss error detection and correction within the link layer. In general, error detection and correction takes place at several layers of the TCP/IP model, including the transport layer and the data link layer or the link layer. Some of these methods are found in one layer, whereas others may be found in another. And so we will talk about several of these techniques. We have just completed in the last lesson the discussion of parity, which is a simple and easy to implement error detection and correction approach. Now we will start with the next one, checksumming. In checksumming techniques, the bits of data in figure 5.4 that we looked at in the last lesson, and you can also find a version of it in your textbook, are treated as a sequence of integers. One simple checksumming method is to simply sum these integers and use the resulting sum as the error detection bits. The Internet checksum is based on this approach. Bytes of data are treated as 16-bit integers and summed. The ones complement of this sum then forms the Internet checksum that is carried in the segment header of the transport layer. The receiver checks the checksum by taking the ones complement sum of the received data, including the checksum itself, and checking whether the result is all 1 bits. If any of the bits are 0, an error is indicated. In the TCP and UDP protocols of the transport layer, the Internet checksum is computed over all fields, header and data fields included. In IP, which is in the network layer, the checksum is computed over the IP header. In other protocols, one checksum is computed over the header and another checksum is computed over the entire packet. Checksumming methods require relatively little packet overhead. For example, the checksums in TCP and UDP use only 16 bits. However, they provide relatively weak protection against errors as compared with cyclic redundancy check, which we're about to discuss. Cyclic redundancy check is often used in the link layer. Why is checksumming used in the transport layer and cyclic redundancy check used at the link layer? Well, remember that the transport layer is typically implemented in software in a host as part of the host's operating system. Because transport layer error detection is implemented in software, it is important to have a simple and fast error detection scheme such as checksumming. On the other hand, error detection at the link layer is implemented in dedicated hardware in the adapters or network interface cards, which can rapidly perform the more complex CRC operations. An error detection technique used widely in today's computer networks is based on cyclic redundancy check codes. CRC codes are also known as polynomial codes, since it is possible to view the bit string to be sent as a polynomial whose coefficients are the 0 and 1 values in the bit string, with operations on the bit string interpreted as polynomial arithmetic. CRC codes operate as follows. Consider that D bit piece of data that we identified with the variable D in the last video. The sending node wanted to send to the receiving side. The sender and receiver must first agree on an R+1 bit pattern known as a generator, which we'll denote as a G. We will require that the most significant bit of G be a 1. The most significant bit is the leftmost bit in the string. The key idea behind CRC codes is shown in figure 5.6 here on the screen. For a given piece of data, D, the sender will choose a number of additional bits, R, and append those bits to D such that the resulting D plus R bit pattern, interpreted as a binary number, is exactly divisible by the generator, or G. In other words, it has no remainder, and this is using modulo 2 arithmetic. The process of error checking with CRCs is therefore simple. The receiver divides the D plus R received bits by G. If the remainder is non-zero, the receiver knows that the error has occurred. Otherwise, the data is accepted as being correct. All CRC calculations are done in modulo 2 arithmetic without carries in addition or borrows in subtraction. This means that addition and subtraction are identical, and both are equivalent to the bitwise exclusive OR, abbreviated as XOR, of the operands. If you would like to explore the mathematics of cyclic redundancy check in more detail, please feel free to do so. The authors do a very good job of it in your textbook, and I'm sure you can find other sources on the internet. For our purposes, we wanted to introduce you to error detection and correction at the link layer of the TCP/IP model. And those include parity checking, not so much checksumming, that's primarily transport layer, but error checking and cyclic redundancy check. That concludes our discussion of error detection and correction. We're about to begin a discussion on multiple access protocols. But before we do that, this would be a good place to stop so that you can get your thoughts together and update your notes on the topic of error detection and correction. When you're ready, come on back and we will begin the next lesson on multiple access protocols.